So first I'm just going to give you all the steps and then we'll do an example of it. So we're going to do separate half reactions for, oops, I'm sorry, for oxidation and reduction. That's what I'm trying to write. Okay, so do you remember yesterday we talked about how to identify oxidation states? Atoms of an element are 0. Monoatomic ions are equal to charge. Fluorine's always -1. For our purposes, oxygen in its compounds will be -2, and hydrogen for the most part will be +1. And then we went through some examples of finding out what the oxidation states of other substances were, because they all have to add up to whatever the overall charge is. That sound familiar? And then at the very end of yesterday, we said, look, this is the step that's oxidation, this is the step that's reduction. And now what we're going to do is we're going to pull those two things apart and write them as separate equations and work on them side by side. All right, so here's what we're going to do. 2. For each half reaction, you're going to do the following, and the order does matter. So the first thing is going to sound familiar. You're going to balance everything but H and O. Okay? Stay away from H and O. And there's 2 reasons why you want to stay away from H and O. Right? One is, do you notice that we said that this is taking place in solution? Okay? So guess what's going to be present? In the form of water. And we also said that this is acidic. So guess what else is going to be present? H pluses. You know what I'm saying? They're going to be there even though you might not see it in the equation. They're there. All right, so we're going to stay away from H and O at first. So we're going to balance all elements but H and O. Sometimes you don't have to do anything here. Balance all elements except H and O. B, the order matters here now. Now you know there's going to be water present, H2O, and you know there's going to be H pluses present. Let's see who's really smart. What would you want to do first, the H or the O?
H.
Now.
Because
What?
they're more up than they're more new.
No, because when you balance the O, you're going to balance the O using H2O. And so when you bring in H2O, what else are you going to bring in? Besides O. You're bringing in H's. So then you'll have to go sew that up afterwards. Okay? So there's a logic why you're doing it in this order. So when it comes to balancing H and O, you do O first using H2O because it's going to carry along with it H's, which you can reconcile later. Okay? So we're going to balance O using H2O. Balance O using H2O. What do you suspect you're going to balance H's with? Using, it's acidic. H plus, yep. So balance H using H plus. So if you bring in H plus, settle the issues with the H's, what problem did you just create by bringing in H plus? What are you messing with?
There's now a charge.
There's now a charge issue, okay? And if you remember, this is a redox reaction, correct? Which involves the loss and gain of what?
Electrons.
Right, so now that's where we're headed now, okay? So now D, we're going to balance charge using electrons. And that's probably the most confusing step in what we're dealing with right now. Balance charge using electrons. And why some guys have a tough time with this, it's kind of like one of those, again, one of those back asswards kinds of things. If I add plus negatives, I'm really reducing it, right? If I add negative things, I'm actually bringing the value down. So when you go to balance using electrons, the electrons are always going to go to the side that's bigger, more towards the positive end. So obviously, +4 is bigger than +2. I'd add to the +4 side. But -2 is more positive than -4. You follow that? It's more to the right on the number line. So I would add to the -2 to bring it down to -4. Get that concept there? We'll do it in practice here in a second. Okay, so we're going to do that to each half reaction. So each half reaction will be separate, and we're going to be doing this independently to each one. One reaction might require me to do one thing, one half reaction might require me to do anything, or something else. But when I get down to the end there, now I got to get these things so they can mix together. So the whole deal is with redox reactions is they're about the exchange of electrons, right? So if I do my two half reactions and one says this thing's giving up 2 electrons and that thing's getting 2 electrons, and I can just smash them together. But if the one says this thing's getting rid of 2 electrons and this one's gaining 4 electrons, well, it's like I can't walk outside, drop a $10 bill on the ground, and then somebody come up and find a 20. I mean, I dropped a 10, they're going to find a 10, right? So whatever the exchange is, it has to be equal. Whatever one thing loses, the other one has to gain it. And so if there's a discrepancy on how many lose or gain, we got to adjust the one that's smaller up to the one that's bigger, or we got to find a common multiple. So we're going to multiply one or both equations. Multiply one. I should say or both. One or both half reactions. One or both half reactions by an integer that makes the electrons equal. That makes the number of electrons in each half reaction equal. Each half reaction. Okay, so now we're going to get them to the point where, okay, if somebody loses $10, then somebody gains $10. That's a reality. That can happen. So if somebody loses 4 electrons, then the other one gains 4 electrons. That can happen. Now I'm going to smash those two half reactions back together because that's my goal, is to balance this reaction overall. So 4, we're going to add the half reactions. We're going to add the half reactions and cancel where necessary. So you may or may not have to do that. And then check to see it's balanced. Check to see that it is balanced. Okay. I'm not going to lie here. It's going to be a little difficult to try and fit it on this screen, but I'm going to do my best. I think I can get it done. It's going to be ugly. Yeah, I know I can do this. Okay. All right, so let's do this now by example. Right, so here's an example. Let's say this is an unbalanced redox reaction. Let's say Fe with an oxidation state +2 reacts with permanganate ion, which is MnO4 minus, to form Fe, which is now in the +3 oxidation state, plus manganese, which is +2. So I guess the first thing to notice is that, like, there's an O on the left side, there are no O's on the right side, where that didn't happen before when we were balancing. But the reason it can happen here is because, again, this is taking place in solution. There's some water present. It's going to be interacting with the water too. So what we're going to go do first is identify our oxidation state so we can figure out what's going on here. So let's see. What would the oxidation state for something of Fe +2 be? Just?
-2?
Not -2.
Oh, no. Never mind. I thought fluorine.
plus 2. It's a monoatomic ion, so it's equal to its charge. So this is, I'll put down here, ox states. Let's see here. Ox states. So this is going to be plus 2. We've got a rule for oxygen in its compounds, or in its substances. Oh, it's got to be negative 2. I'm not going to show you that. Negative 2. So I'm going to, let's see if we can figure out what permanganate, or what manganese is. Each O is negative 2. How many of them do I have? 4. What's that total?
-8.
Negative 8. This whole thing has to add up to
-1.
negative 1. So if this all adds up to negative 8, then that must be
+7.
plus 7. How many guys can digest that? Got to all add up, okay? If you have trouble with that, that's going to be a big problem if you can't figure that out, okay? And that's what we'll practice here after we do this example. So this is plus 7. What's this Fe plus 3 going to be? No, that gets it. Plus 3. And then what's this manganese going to be here? Plus 2. Okay, now, let's say you went and looked and none of the oxidation states changed. That would mean it's not a redox reaction. There's got to be a change because there's got to be electrons being exchanged. So let's see something that changes. Here's something that changes. Fe goes from being plus 2 to being plus 3. So that's a change. And manganese here goes from being plus 7 to plus 2. Oxidation involves oil rig. Loss. So who's losing electrons?
Fe. because
Fe is.
It's gaining a positive.
Yep.
Yes.
You got to think backwards. So if this is plus 2, if it loses a negative, think about that. That's a double negative. Losing is a negative thing. A negative is a negative thing. Losing a negative means you get a positive, right? Like, I'm not going to do that. Means I am. Right? Okay, so this thing is going from positive 2 to positive 3. That's being oxidized. Or oxidation. For some of you guys, it might be easier to spot reduction first. Because look what happens to the number in reduction. Plus 7 to plus 2. Didn't it reduce? So if you have trouble, just get in your head, I'm going to do the reduction first. Should go down. Therefore, oxidation better go up. So this is my reduction. Okay. All right, so here's where I'm going to run into a little problem. I'm going to do my best here. Let's see. Actually, it's not going to be a problem. What I'm going to do, okay, I can fit this on a width of paper, no problem, in my notebook. Like when I'm writing in a notebook, I can fit it across the width, okay? So one thing you want to keep in mind is that you want to keep them kind of small at first because you're going to be building out on either side of these equations, okay? Now on this thing, it's kind of hard to write like that. So what I'm going to do, just for now, what I'm going to do is I'm going to write 1/2 reaction and have about that much space for it. And then I'm going to slide over and probably have about that much space for the other half reaction. Just so you can plan for space here. Because it is, I don't want to show it to you differently because it's much easier if you're doing it right next to each other. I mean, much, much easier. So let's go. So now I'm going to split these into 2 half reactions. So I like to do my oxidation first. It's just the nature of habit. So what I'm going to do is I'm going to write down, again, I'm going to start in from the left side of the paper a little bit. So I might have stuff to write to the left. But I want to save room on the right of this equation because I might have to add things to the right of that half reaction. So my first half reaction goes like this. It's Fe is plus 2 going to Fe, which is plus 3. See, I'm just drawing the connect the dots between the two things. That's my oxidation, and then I'm going to come over here a little bit. I'm going to scroll in, and my other half reaction is MnO4 minus going to Mn plus 2. So there's my 2 half reactions. What did the first step say to do? Balance what using what?
Using
Okay, balance all the elements but H and O. How many FEs are here? How many FEs?
One.
One. How many FEs are here?
One.
They're in balance. So a lot of times you're not going to have to do anything. Right? You'll see examples where you will. How many MNs are here? How many MNs are here?
One.
So we just didn't have to do anything in this example. And you might think, well, Mark, that's a pretty crappy example because you're not doing that. But that's the point that I'm trying to make, is that many of these problems you have to do some steps and not others. And you'll see variations as you go through homework. Yep.
If there's like an oxygen on the left and there's none on the right, how are you going to
Okay, what's the next step?
balance them using H2O?
Balance O using H2O. All right, so do we have any O's here?
No.
Nothing to worry about. But we have 4 O's here. So to balance up the O's, how many H2Os am I going to put in there?
2.
No, because that only bring in 2 O's. 4 H2Os on what side? The right side. Okay, so I'm going to do this, and this is the way maybe you should start, is I'm going to rewrite every line that I do. You can get to the point where you just start bouncing back and forth. The problem is if you make a mistake, it's tough to unravel where you went wrong. So with this one, the MnO4 minus yields Mn plus 2 plus 4H2O. Because it's in a solution. It's in water. I know that that water is there. But again, still didn't have to do anything to the first equation. The first equation just has Fe. There's 1 and 1, so there's nothing to do. Next step says balance H using H plus. So again, no H is over here, right? Nothing to do.